So this is turbulence. We'll move to turbulent combustion. Yeah. I have a movie here. I'm not sure if it's going to play, but I can try. So this is inside like an aircraft engine. That's a swirl injector. It's injecting liquid fuel, and then it burns there. And on the right-hand side is a lower Reynolds number flame similar to that. Now, if you have seen laminar flames, like a candle, right? Compared to that, these flames are complex only because they have these intermittent structures. There are turbulence tries to change the flame shape. It makes it, it contorts it, right? So it's like it's pulling it in different directions. And this is all those eddies that we saw before interfering with where reactions are happening. And then as a result, they're either stretching it, they're making it weaker, or sometimes they're making it stronger. Right? So they have all kinds of interactions that's happening here. So this is the main idea that we want to look at. Now I'll run this with very little expectation it's going to work. Oh, it works, okay. So if you guys have not studied gas turbine, that's it. This is the whole movie. So yeah, there's nothing else coming. Yeah. So this, by the way, took whatever the biggest supercomputer that was there at that time to run for many months, to get to this. So you have a fuel injector, and then there's a core where you see that red stuff, and that's where things are burning, right? And then if you had observed in the short time, there's something coming from the top hole further down from the core. So I'll run it one more time, and you'll see what's happening there. So you can see that there's this dark fluid coming from the top. So if it's red, it's hot. If it's dark, it's cold, right? So that's what this picture is. And so this is what is called an RQL combustor. So you have a rich initial zone where you burn it very rich, right? Most military aircrafts operate like this. Then you have this secondary air that's coming in, which quenches or reduces the fuel-air equivalence ratio. And then it gets it close to stoichiometric or something lower than that. And then you burn it lean further downstream. So that's the RQL design. And then downstream of this sits turbines. They spin and then whatever. That's what you do. Typically, a turbine says, I don't know of a device that will operate like this without a turbine, but maybe there are. Who knows? But what you see is that this is not a single flame front. It doesn't look like a candle. It's very complicated. It's a fireball, right, to put it mildly. And it's volumetric. Yeah. And if I slice it across and see it, I will see these high temperature regions all across it. So it's a very volumetric flame that sits there. And it's burning all around. And of course, further downstream, it has a separate flame structure that's not even obvious from this plot. So there are other things that are going on. So this we have to understand. So all that structure that you see is created by turbulence. It's trying to somehow introduce its eddies into the flame and trying to change something about it. And so we need to understand how to think about it. So that's this part of this lecture for the next 30 or 40 minutes. And then we'll go to large eddy simulation and how to think about it using the same ideas. So you might have seen this in today's lecture, or maybe you haven't, I don't know, but you'll see it eventually. You can think of a laminar flame, something, let's say, that looks like this, but even more lower velocity, let's say. And you will have these kinds of structure. There's some inner cone, and then there's an outer layer where you see the luminous part of the flame. And what we want to understand is how to characterize this particular configuration. And one simple way to think about it is to say that I have some cross-section for the flow that's coming in, and then there is flow going out of this. And then I can say, using simple conservation laws, what is the shape of the cone? Like, what should be the speed at which everything is getting consumed so that I can have this laminar, like, flame sitting there? And that gives me the quantity SL, the laminar flame speed. Now, there are many intricacies to how laminar flame speed is defined, under what circumstances, what happens if you stretch it or if you do other things to it and so on. So those are all aspects of research. There are hundreds of papers written on this. For our purposes, those details are not critical. All we need to understand is that if you give me a fuel property and some operating conditions, pressure, temperature of the fuel-air mixture before it enters the flame zone, I can have a single quantity called laminar flame speed, this SL quantity, similar to Reynolds number or eta or these kinds of quantities, to sort of understand how these are related. That's all I care about. Okay? So it's only within this context. The details of this you're going to see in Professor Matlon's class. He's going to teach it all during the week. Okay? So for now, all we care about are these simple quantities, so we can make a relation or we can somehow compare them with eta. And this movie will not play. That I know for a fact. Okay? And the first feature that we have to understand is that if you have this flat flame or something that looks like a very nicely defined stationary flame, the moment you introduce turbulence, it's going to distort this flame. Okay? And it's going to distort it. And when it distorts it, what happens is that area of the flame changes. And when the area of the flame changes, the rate at which you're able to process fuel-air mixture changes. So the area is proportional to how much fuel-air mixture you're burning. So the biggest impact of having turbulence here is that you're able to burn the mixture faster. So which means that in a same area, let's say, of the combustor, or same volume of the combustor, if you now introduce turbulence, you can burn a faster or a higher flow rate of fuel-air mixture than if you had just a laminar flame. So you're increasing the burning rate that you can have for this mixture. So what this tells me is that if I want to design a combustor, I care about the volume that combustor takes and how much power that combustor can deliver. So I need to be able to take the same volume and then be able to provide as much power as I can. So I want to burn things as fast as I can with minimal losses. And so now turbulence becomes handy. It's able to change the rate at which you can burn the fuel-air mixture, so you can burn more inside the same volume. Okay? So the rate at which you're increasing it, now you cannot use this quantity SL anymore. We use this quantity ST, which is the turbulent flame speed. So instead of the laminar flame speed, you now have the turbulent flame speed. So you have a laminar flame speed that's only a property of the chemical mixture and, let's say, the operating conditions. Now you have a turbulent flame speed, which depends on the amount of turbulence you have and how it interacts with this flame. Okay? Now, the game in town is to relate ST to SL. How do you relate that laminar flame speed to this turbulent flame speed or the turbulent burning velocity? And it turns out to be a complex game because there are no clear answers to it. Because many things happen when you introduce turbulence. And it's not always clear what impacts what is the real effect, and so on. So there are regimes in which turbulence can impact laminar flame. So it's not always the same. It depends on how fast the laminar flame is burning, how much turbulence you're introducing, what length scale and what Reynolds number at which you're introducing this turbulence. Right? So all of this becomes critical. Because the Reynolds number at which you introduce turbulence and its length scale, L0, now dictate what eta you're going to get, what Kolmogorov length scale you're going to get. Right? So you have to be able to compare these. So that's very important. So what you have here is this turbulent flame speed and the laminar flame speed, and you have to somehow figure out what's the relation between them. Oh, it actually works. Okay. So my prediction abilities are not very good. Should not be doing computational modeling. So that's a turbulent flame, and you can see that if you just look at it 60 frames per second, which is I think the normal speed at which it's running, it looks blurred, but you can see that shape of it over which it's moving. If you take a very high speed image of this 5 times higher frequency capture, you see that the flame front is more well-defined and it's moving around because of the turbulence. Right? So if I were to open the shutter of the camera for a minute and then keep it, you will just see a single flame that looks like a laminar flame, but a large blob of reactive mixture. Reactions will happen all along this blob. Right? So the longer you open the shutter of a camera, the more time averaging you're doing. So it will look like a time averaged image of the flame. So it looks very different. So how do we relate this? There are many different ways to think about it. The first one is the Darm-Kohler analogy. So you say the turbulent flame speed divided by the laminar flame speed is related to this U prime or U0, the integral, the eddy is spinning at some speed, fluctuations, so however you characterize that eddy, that velocity controls what turbulent burning velocity you're going to get. So which means that if you were to increase that velocity a lot, you can burn things very quickly. In fact, if you increase it by a factor of 1,000, let's say, right? So if U prime is increased by a factor of 1,000, you should be able to burn the flame at 1,000 times the original value, or so is the thought process. Unfortunately, that doesn't happen, okay? So what we figured out was, if you keep increasing that U prime, so U prime divided by SL just to normalize it, if you keep increasing it, it saturates. So there's only so much you can make the flame burn faster. At some point, it gives up. It doesn't keep up with what you put into turbulence. So there's a limit. It doesn't matter what you do with turbulence. It doesn't matter how you put in the turbulence. There's only so much you can make this flame go faster. Best case estimate, about a factor of 10. Most of the times, you're going to get lower than that. So if your laminar flame speed is in meter per second or centimeters per second, you're now burning at 10 meter per second max, right? The velocity at which the flame will rush through unburned fuel mixture is 10 times what it was with a laminar flame. So you can burn it faster, but there's a limit to it, right? You cannot keep increasing turbulence. So you have to know how to modulate the turbulence. If you think, I'm just going to dump all the turbulence and hope that it'll going to go fast, it will not do that, okay? In fact, it will enter a different regime, and then you might have what's called a detonation rather than what you have, which you want to avoid if you're not designed for this. So that's like a bomb. So if you take a pipe and you keep it all laminar and you light it, the rate at which that flame moves from one end to the other end will be SL, let's say. You introduce some amount of turbulence and you watch the same front move, that will be ST, okay? If you make it really turbulent and you light it up, it's going to start moving at very high speeds and will transition to what is called a detonation, which has a shock wave. At that point, that pipe becomes a pipe bomb, right? So you do not want to get to that state. So most of what we do, you see the x-axis here, that U prime over SL is a factor of 2.5 or 3. So SL is at meter per second. So U prime over SL, if it's a factor of 3, it's about 3 meters per second. Not a big deal, okay? In most of these flows, the acoustic speed, the speed at which sound propagates, might be like 300 meters per second or so. Compared to that, all of this is small, right? But if you make U prime 100 times larger, so now you're approaching the speed of sound for U prime, then you have a problem. So what you do not want to introduce turbulence that will get you to that limit where U prime becomes very large. Right? So you will keep, all your analysis, everything else you do, you have to make sure that your U prime remains very small compared to the acoustic speed. It can be a little bit higher than SL, but not more than that. Okay, so now comes a lot of math. You don't need to know the math. This is all division and multiplication. I'm sure you guys mastered it already. It's very simple, but it's a way to think about the problem, okay? Now, Kolmogorov had Kolmogorov's hypothesis. So in turbulent combustion, we needed to have our own ideas. So we built regime diagrams. So this is a common pastime to build regime diagrams. And there's a very famous regime diagram by Williams, which is what we're going to look at. And there are variations from this, from Borghi, from others, and so on. And to do this, we have to define some numbers. So we take Reynolds number, our favorite non-dimensional number, and we write it slightly differently. So it's still U prime L0 over nu, similar to what we did before. But then if you do some jujitsu, you'll get this. U prime over SL, the x-axis in the plot that I showed you, times L0 over delta L, which is very interesting, right? So U prime over SL is how much turbulent eddy fluctuations that velocity is compared to the laminar burning velocity. So it's a ratio of velocities. Delta L there is some kind of flame thickness. So L0 is your integral length scale, and delta L is your flame thickness. So that's a ratio of length scales. So Reynolds number is nothing but a ratio of velocity scales times a ratio of length scales. So you can rewrite it like this. Okay? And I'll define another one called Damkohler number, which is a ratio of time scales to begin with, T0 over Tf. T0 is the integral time scale, L0 over U prime, things like this. Tf, on the other hand, is a flame time scale. So you take the thickness of the flame, delta L, in meters, divided by the flame velocity, SL, and you're going to get a quantity that's in seconds, and that's your Tf, the flame time scale. So you can take this Damkohler number, do the same kind of math, right? And you'll come up with something that looks like this. It looks very similar to this, but it's deceptive, right? So that's U prime over SL for this guy, for Reynolds number. For Damkohler number, it's SL over U prime, right? So it's a little different. So then you can do more of this, and you will introduce what's called a Karlowitz number. So Karlowitz number is similar to Damkohler number in the sense that it's also a ratio of time scales. But now instead of this being related to T0, right, the integral time scale, it's related to the Kolmogorov time scale, T eta. Okay. So again, going through this math, you can show that Reynolds number is just the product of Damkohler number and Karlowitz number squared. So this is the main relation to get from this. So what we have done now is I introduce two additional numbers. We had Reynolds number to begin with, and now there's Damkohler number and Karlowitz number. Okay. Using this, we want to know what will happen to the flame in different regimes. What happens when eta is very small compared to delta, the flame thickness? What if it's moving very fast compared to U prime? So those kinds of limits we can analyze, right? So that leads us to some more quantities, but I'm going to skip this slide for now because it's not very critical. When you think of a laminar flame, I don't know how many of you have taken a course in laminar flames or something in this, so I do not know. So truly, this is my way of explaining it, and you will see this. I think Matlon has this later in the week, so it's not coordinated like that. So if you take a laminar flame, and you probe into what's happening inside that flame, okay? Of course, using computations, you can do this using experiments also. You'll find this characteristic plot. So the x-axis here is just the x-axis going across the flame, okay? So the flame is located around 0. So that's where everything is happening. And what you typically notice is that in a laminar flame, the temperature on the unburned side, so the unburned side is on the left, everything is burnt and goes towards the right. Yeah? So on the unburned side, the temperature starts going up even before you hit the flame, and that's because there is thermal diffusion. So that's what brings the temperature up. So as the temperature keeps going up, it prepares the fuel-air mixture to burn when it reaches that flame front. Okay? And once it passes that front, then it does a little bit more heat release, and it reaches the final temperature, which is TB. That's the burnt flame temperature. So it goes from unburnt temperature to burnt temperature. This is across a flame that's sitting at 0 position. Okay? So fuel, on the other hand, has to do the opposite. So fuel and air are rushing towards this flame, and as they come towards the flame, this higher temperature is going to start making them react. They're going to break down, and all the reactions are going to start. This is what Professor Karan is teaching right now in the other room, right? So that's chemistry. So you can see that if I look at methane, CH4, its concentrations are starting to go down as you go towards the flame, right? And then it gets to 0, and then it's gone. So there is this critical region close to zero where a lot of more important things are happening. This is the region that is the inner core of the flame, and this has to be preserved in order for the flame to stay stable. If you somehow destroy that inner region, which maintains the balance between the heat going out and the chemical reactions, all the flame will just not stay anymore, okay? So that inner core has its own length scale, and that's the other delta that you have. So you have delta L, which is the full thickness of the flame, and then you have this delta, which is the inner layer of the flame where this balance holds, okay? So the delta is typically smaller than delta L. So we have a Karlovitz number for delta L, which there is no subscript, and then there's a Karlovitz number for delta based on the inner layer thickness, where you have this subscript delta and then delta by 8. So this is definition and how the flame structure looks. So now what's going to happen is that you have eddies of size L0 all the way to eta, and the question is what happens when they come rushing towards this flame? What is it going to do towards this flame? So then you get this plot, which is called the regime diagram. So you see that I plotted this, not I plotted this is how it's plotted. U prime over SL, also in log coordinates, these are all log-log plots. And the x-axis is L0 over delta L. So the x-axis is the integral length scale divided by the flame thickness, that's delta L. Y-axis is U prime, which is the turbulent velocity, divided by SL, which is the laminar velocity for the flame. And you have these different regions, okay? So what we saw before is that as you keep changing U prime over SL and L0 over delta L, you get different Reynolds numbers, because Reynolds number is just a multiplication of these scales, right? So as you go along these plots, you're now going to get many different regimes. So Reynolds number of a constant value will look like a diagonal. So you see that RE equal to 1 plot. So that's when Reynolds number is exactly equal to 1. Every other Reynolds number, higher Reynolds number, will be lines parallel to RE equal to 1, but further and further away from it, towards the top right plot. So as you keep increasing Reynolds numbers, you're going more and more towards the top right on parallel lines parallel to RE equal to 1. Okay? Then you have Karlovitz, which has a slightly different straight line. So the Karlovitz equal to 1 line is this diagonal that looks like this. So it's not orthogonal, but it's different from the RE equal to 1 line. So as you increase Karlovitz number, you're going to have lines parallel to Ka equal to 1, but more and more towards the top left of the plot, right? So you're going to have RE, higher Reynolds number going to the top right, higher Karlovitz number going to the top left, as you keep having these parallel lines. Okay, so I will leave this here, and I'll tell you what happens for different devices, and then what are these regimes actually mean overall. So this is actually from a very old plot. So I don't think things have changed all that much in operational characteristics, but everything might have been pushed a little bit to the top right as time has progressed, but otherwise they're roughly the same. So what you see here are gas turbines which operate at high Reynolds numbers. And so you can see that RE equal to 1 line is this line at the left plot. So it's parallel to it, and so it's going at a much higher value. The same way, they also operate at higher Karlovitz numbers. So that's why it sits at the top right there. Internal combustion engines in general operate at a lower Reynolds number and a lower Karlovitz number. So it doesn't use turbulence the same way as a gas turbine does. So you can see that its range is a little bit smaller than what you have with the gas turbines. There are also this rhomboid picture in the middle, which is where all the experiments could be performed at this stage, right? So that's where all the experiments sit. So typically the experiments do not reach what you have for the gas turbines. That's very hard to do. Simulations also don't reach that particular region. So most of what you see is towards the lower Reynolds number, perhaps towards higher Karlovitz number, but by compromising on the Reynolds number. So this is the regime. These are the regimes you see. So what happens in these regimes? Each one of these regimes has a particular name, and there are different things that happen in this. And you can think of all of them using that picture on the right-hand side. So you have some flame, which is the reaction zone that's written there. In front of the reaction zone lies the heating zone, the preheating zone. Okay? And in front of the preheating zone is the unburned mixture. After the reaction zone sits the burned mixture. So when you have eddies come and hit this flame, they're going to somehow contort this flame surface. And depending on the size of the eddies, you can have very different behaviors here. Okay? So you have the wrinkled flames in which turbulence is very weak. So Reynolds number is very small. So it's not very high, it's very small. And you have flames that almost look like laminar flames. They're just stretched a little bit. So it will look something like this. So they're moved around. You can think of like a piece of cloth that just wrinkled, right? So that's what the wrinkled flames say. So there's not a huge change in behavior of the flame, and it's roughly the same as what you see in the laminar flames. From there, you go to what are called corrugated flames. In the corrugated flames, turbulence, especially turbulence of certain sizes for the eddies, are able to really change the flame structure, right? And so they are able to make the flame surface become much higher than what it was before, okay? But still, the eddies are not small enough to directly affect the flame zone or where the reactions are being present. So if the eddies are big enough, they cannot penetrate that reaction zone very quickly. Okay, so the eddies are still big. Now you have to remember, for the same device, as I keep increasing Reynolds number, L0, the integral length scale, where the peak of the spectrum is, it stays the same. It doesn't change very much. But what changes is eta, right? So when I'm at very low Reynolds number, my eta is still very large. So the spectrum is very compact. L0 is the same, eta is very large. So it's not able to do anything to the flame. As I increase the Reynolds number a little bit more, you get into these corrugated flames. If I am able to increase it even more, if the Reynolds number increases even more, I get to the thin reaction zone. In the thin reaction zones, the preheat zone where you see the temperature going up, the eddies are big enough to come into that zone and mix that material. So instead of having a thermal diffusion that's controlled by a Fick's law, now you have eddies that are changing that structure. So you have a much more complicated structure in the preheating zone than what you have just for a laminar flame. Now past this is the broken reaction zone. This requires very high Reynolds number to get to this zone. And when you do this, turbulence is so intense, it's able to penetrate through the reaction layer, and it breaks the flame into pieces. So it actually shreds the flames, and you get many small pockets of flames or broader regions over which the flame burns, and so on. Now that part, what happens to the flame, is a matter of speculation. It's very difficult to get to that broken reaction zone regime experimentally or simulation-wise. So there are multiple theories for this. If you're interested, there's a review paper by Jim Driscoll on these high Karlowitz flames, which is how you get to the broken reaction zone. And it's not a direct thing that the flame shreds. In fact, if I show how these flames look for the different Karlowitz numbers or Reynolds numbers, I'll go back to this. So this is all from DNS. There are 3 panels of data here, 4 snapshots for each panel. So there's density, that's the 4 here. There's the burning rate, which you can think of it like the burning velocity. And then you have temperature, which is here. Okay, it's oddly plotted, right? So it's standing vertically. So the flame is progressing, towards it's progressing towards the bottom, right? So you have density here, and the burning rate in the middle, which tells you where the flame is located, and temperature. And if you look at temperature is low at the bottom, and it increases at the top, right? So the flame is moving from the top towards the bottom, and it's burning everything afterwards. So what you have in these 4 panels are different Karlowitz numbers. So we saw before, Karlowitz number is the ratio of length scales. So if I go back, So you can see the Karlovitz number there. That's delta L, laminar flame thickness, divided by eta, right? So if eta becomes smaller and smaller, if your Reynolds number increases, then your Karlovitz number is going to increase. So what they've done in those simulations is to hold everything else the same and increase only that ratio between the laminar flame thickness and the Kolmogorov AD size. And you see that at Karlovitz of 10, that's the wrinkled or the corrugated reaction zone. So the flame is stretched and it's moving around, but turbulence otherwise has no big impact. But as you go to higher and higher Karlovitz numbers, you see that the flame front is not the same. In fact, at the highest Karlovitz number, everything is shredded, and you get these very volumetric heat release over a much larger region. So the point to remember from this is that when you have higher and higher Karlovitz numbers or higher and higher turbulence, it's going to start impacting how the reactions actually take place. Okay? So that is the core of what is called turbulence flame interaction. Now, because these flame fronts are very thin, these interactions are also happening at very small length scales. They're not happening at the device level meter length scales. They're happening at micrometers or tens of micrometers or even up to a centimeter, but not more than that. They're not much larger than this. Right? So these turbulence flame interactions are necessarily at the small scales, and so that's what poses the biggest computational challenge for us. So that's what we have to think about when we do modeling. Yeah. So this is all I had for the combustion regimes. Before I go to large area simulation, any questions on this topic at all?
All the questions, like all the conversation around the regime background, like on the y-axis, we always talk about that. So, like, how do we go about thinking about regime diagrams for non-units?
Yeah.
Because when we talk about application, we always implement one. We would want to put our operational point instead of regime first. So how do we think about that?
So the question is about laminar flames and diffusion flames or non-premix flames. Do you guys know the difference about it? If you don't know, in diffusion flames, fuel and oxidizer come from different pipes, and then they mix while they react inside the combustor. In premix flames, like what we saw here, you mix fuel and air ahead of time, and then you inject into the combustor, and then they burn there. So they are different physics. They represent the two ends of combustion processes. And typically, if you have an aircraft engine, you would not run it in the premixed regime because you do not want to mix fuel and air even for a short amount of time and keep it outside the combustor. That's the most dangerous thing you can do, right? So typically, aircraft combustors operate mostly in the diffusion flame or the non-premix regime where fuel and oxidizer are independently injected into the combustor. Gas turbines for power generation, land-based gas turbines, they operate using premix combustion because there, it's not that it can be unsafe, but there are other ways to mitigate risk that you do not have in an aircraft. Aircraft engines have to be compact. Land-based engines can be as big as you want, things like that. So there are other ways to mitigate it. So the question is, no, this is just my prelude to answering him. I'm not even close to answering him. If all of what I talked about is for premix flames, how do you use it for diffusion flames? And the simple answer is that diffusion flames are controlled by other characteristics. There are other kinds of quantities that you need for that. So it may not be flame thickness there. It's the strain that will extinguish the flame compared to the Kolmogorov velocity, for instance, or Kolmogorov time scale that you have. So you have to have different quantities to figure out whether flames will extinguish or stay lit. But in some sense, the impact of turbulence in diffusion flames is a lot easier to understand than it is in premix flames, which is why you have this complex flame diagram here. So there, the response to strain is what controls the diffusion flame.
Do we have like a similar regime?
Not similar one, but there is a regime diagram. There's a different way to think about what can happen to diffusion flames here.
So you mentioned before, if you increase your turbulent
No, they're not. So in fact, they're two ends of the same process. And so this I think is in Wednesday's lecture. So you can have a continuous map between deflagrations, what these are, flames, and detonations. It's simply that the intermediate region where they go from deflagration to detonation is not smooth. It's not like every point is accessible. So it deflagrates, it stays in a region, and then suddenly becomes a detonation. So there's a jump between the processes. Anything else? Because it's pure math at this point. So this is the wrong time to say. It's very hot in here suddenly. I don't know what happened. Okay, so keep this in mind, what turbulence does to the flame, right? And what regimes you have. What we'll do next is look at large area simulations. And before I go fully into the details of it, I do want to talk a little bit about computational modeling based on all the things we have seen so far, and that will set up what we need to learn for large area simulation. Okay, so we now know certain quantities. We know eta, right, Kolmogorov length scale, which becomes very small if Reynolds number increases. So that's our fundamental limitation. We also have chemistry, how fast heat is released, and that's connected to fuel oxidation, all these processes. So there's a time scale there also. They are all the time scale for fuel oxidation can be very fast, and so there's a rate at which you can update your equations that has to become very small. So your time steps have to become very small because of this. So there are these conflicting needs for computational approaches. Okay, so I've written these equations. These equations are not perfect. They have a lot of assumptions. So if you guys know Navier-Stokes equations, you should be able to figure out what's wrong with them. Do you guys know what's wrong with them? I made some extraordinary assumptions in writing these things down. So what do you know? Can you point out? I did not make a mistakes in indexing. Okay, that I'll tell you. Could be something else. I removed. I didn't catch it. It's always 1 over rho dp dx, right? Okay. I did neglect gravity. Why do you think I neglected gravity? So what number would characterize my ability to get rid of it? Do you know? Yeah. So yeah, I'll assume that gravity does not matter. Yeah. Because these things are relatively fast, so it shouldn't matter. Anything else? So we often read equations by context. Like we've seen them, like the way we read words on a paper, right? We don't really read the words. We know those groupings of letters, what they are, and we have memorized them so much that if I make small mistakes in the letters, you will still read it as if it's the right word. So this is a common test that's given. I've done the same trick for equations here. So you guys all have seen it. You sort of know that there should be gradients and there should be rho and u. And if I'd put u in the denominator, you would immediately say, oh, that's not correct, right? But there are a lot of other assumptions. So one of the assumptions I made, if you look at the species equations, right, I've written as rho times di, dyi dx. So I is the species index. So if I'm doing chemistry, there could be 30 species, so I will be 1 through 30, okay? I've attributed a diffusion coefficient to each one of those species. And I'm saying, by writing it as d underscore I, that they're all different. They could be different, okay? Now, what happens if I sum up all the equations for species? What should you get if I sum up all the equations? Do you know? What is it? The yi is the mass fraction. What happens if I sum up the mass fractions? What is it? It's conservation of mass. So sum of yi is 1. So if I add all the equations, I should get continuity equation, which is the first one. But will you get it? You won't get it, right? Because the diffusion term has this di, it won't go on. So I've assumed incorrectly that these species equations are consistent with the continuity equation. These are important. I say this not because, I also didn't want to change the equation. It takes a lot of efforts, but that's not the point. It's simply that these minor things, right, you would think, how can this be important? This has a very important effect in how you simulate flames. So you have to be careful about these details. The same way for temperature. Do you know what assumption I made for temperature? I'm also made like arbitrary assumption, not just Lewis number equal to 1. Lewis number with respect to every species is equal to 1, even though every species has a different diffusivity, which is completely nonsense. Yeah? But I made another big assumption.
With the thermal and the mass diffusivity are the same.
Yeah. No, but then I wrote in the previous equation they're not the same. No, I assume Cp, specific heat capacity, is a constant, and I took it out, and I divided thermal diffusivity by specific heat capacity, and then I wrote this thing. So if you simulate this, you will not get anything close to a flame, right? You'll get something that looks like a flame, but it'll all be wrong. So be careful with the equations that are written down. So I say this as a reference, but it's not truly a reference. So you should remember this whenever you look at these slides, that these are all incorrect. Now, it turns out that you can write the conservation equations for a reacting flow in many, many different ways. So there's a very famous book by Professor Poinsot, and he usually teaches this course in other years. And in that book, there's a page with all the different ways you can write the energy equation, all the different ways you can write the conservation equation. So you should take a look at this. The choice of how you write this energy equation really depends on what problem you're trying to solve. If it's a gas turbine engine, I would write it similar to this without a lot of error, or without making a lot of error. But if it's a high-speed reacting flow, this equation will look vastly different. Okay? And the choice you make depends on the solvers you have, what physics you want to capture, things like this. So there are many ways to write this equation. So you should be aware of that part. Okay? Now, the best way to think about all the approaches that we have, high fidelity simulations. The most common one is direct numerical simulations. As the term says, you take these equations, the correct ones, you put it on a computer, and then you say go, right? And then it gives you all the results. So that's DNS. There are some subtleties to DNS, and this is not critical right now, but you see these last bullet points like this, these will come to tomorrow. When you do DNS of a flow, you are simulating one realization, one flow where you have some initial field, you evolve it over time, and you see what it looks like at a future time. If my initial conditions change even a little bit, I will get a slightly different field at later time. Maybe not slightly, maybe a very big different or a large difference in fields I'll get at a later time, right? So it's possible. But all I'm doing is one such case. If it's a statistically stationary flow, which means that once I simulate for some time, the statistics of the flow do not change. The mean temperature, the mean velocity, they do not change. That I call, those flows, this single realization doesn't matter because I can time average it and they will all look the same. So DNS is solving those equations directly on a computer, most likely a supercomputer. The problem is we don't have that supercomputer for if your problem is too complicated. So we saw this before. To solve this on a machine, you need some kind of CFD, grid-based CFD, let's say, and which means that the grid should be spaced smaller than eta. Okay? So if you have a domain of some length and your grid has to be smaller than eta, the number of grid points in each direction is L divided by eta, the length of the domain divided by eta. You cube it, that's L divided by eta whole cube. This is the Kolmogorov scaling law. So L divided by eta is proportional to Reynolds number power 3 over 4, right? And so if I cube it, I get Reynolds number power 9 over 4. Now, time step in any CFD is linked to the grid. That's the CFL criterion, if you guys have taken CFD courses. So I cannot take a big time step when my grid is very small. So my time step is limited by how big my delta x is. So it adds another Reynolds power 3/4 factor to it. So the cost of a simulation is Reynolds cubed. Okay, and this is this cannot be overcome. Okay, this is as simple as that. Our computers are fast now, and we can do some simulations, whatever. But the fact that when you double your Reynolds number, your cost goes up by almost a factor of 10. It's just too much. It's just too much. Okay. And in the last 10 years, last 10 years, or even a little bit longer than that, our supercomputers have gone from about, I wouldn't say 10 petaflops, whatever that unit might be, 10 petaflops to, let's say, 10 exaflops. So that's, if you know the math, is about a factor of 1,000. So it's 1,000 times faster, okay? So which means if I take the cube root of it, I can do Reynolds number that's 10 times higher, okay? So all the machines in the world, all the things we have done, I can go to Reynolds number that's 10 times higher, okay? So we'll see where we are right now. So this is from 2007, and I give it as an example of how things have changed, right? In 2007, there was something called the Earth Simulator, which was a supercomputer, and they would take 2,000 processes, and you see this number, 16.4 teraflops. One petaflop is 1,000 teraflops, and one exaflop is 1,000 petaflop. So right now, the machines are about 1 million times faster than what it is here, okay? So which means that we can do Reynolds number that are 100 times higher compared to what we could do in 2007. And in 2007, our Reynolds number that we can do was already not that great. It was, it was relatively small already. But that's the change that we have right now. I'll tell you what the possibility now is, right? So this is from 2014. That is 10 years ago. And at that time, we could do in a channel flow, this is from a channel flow, a Reynolds number of 125,000. So this is U times channel width divided by, not turbulence, this is just a solid standard Reynolds number. 125,000. Typical gas turbines, if you do the evaluation, it'll be at a Reynolds number of about 10 to 20 million. So that's what you'll have around takeoff conditions, okay? And when I say 125,000 is what we can do 125,000 for a non-reacting flow in this kind of simple geometry. If you take a gas turbine, it's very complicated geometry. It's reacting, right? Clearly, that's why we're here. It's a turbulent combustion. On top of that, it has liquid fuel being injected. So if you add all of that complexity, maybe you can simulate 3 to 4 times this Reynolds number with the current technology than we could do before. So we're still 2 orders of magnitude difference in Reynolds number from what is possible. So 2 orders of magnitude difference in Reynolds number means that it's cube of that, right? So we need 1 million times more powerful machine before we can simulate any of these geometries, okay? It took 20 years for this million increase in compute power. Maybe it'll take faster the next 20 years, who knows? But it's still a bit away. Okay? So it's not easy to simulate this. Now, this is a map of how things have changed. And you can see on this axis how compute power increases with time. So in 1996, The 3 lines here, sorry, but I don't have the labels for them. So essentially, the top line is the fastest machine on the planet. Okay, that's the blue line. The bottommost line is the 500th fastest machine. Why 500? Because it's a list of 500 top. That's what this list is. It's a list of 500 top machines. So that's the 500th machine on the planet. And the middle one is the median one. So that's what tells you, on an average, where things are. So 1996, we were at terascale. It took 12 years to get to petascale. So that's 2008. I think what happened was we were supposed to reach exascale by 2019 or so. And then there was COVID, so it was a little delayed maybe. But then AI took over, and then that curve accelerated. So we are now at 10 exaflops already. So we are at, this ends at 2020, but at 2024, already we were at 10 exaflops. So, but there are some, there's some funny math in all these calculators. It's not truly 10 exaflops, things like that. But the machines have gotten faster at the same rate. So this is where we are. So it's not that there's some sudden jump that will take you to very large values. Yeah. Now the problem, we saw this before, you also have the reacting flows where the chemical source term imposes its own time constraint. So you cannot just solve these equations as fast as a non-reacting flow. And so there's a regime diagram for this also. And this is a very old one. And I put this here because nothing really has changed. It's really roughly the same. So on the x-axis is Reynolds number. And so as things get faster, you can simulate higher and higher Reynolds number. On the y-axis is Damkohler number. So how fast is your chemical reaction compared to your integral timescale? So that's Damkohler number. Okay? And so if reactions are faster and faster, the Damkohler number will become bigger and bigger. Okay. So what you see is that you can simulate non-reacting flows. Damkohler numbers that are small or close to 0, you can go up to 1,000 on the scale. But the moment the Damkohler number becomes large, because you have to capture all those scales also, your grid has to become much finer, and then it starts going towards the other end. So if you keep increasing Damkohler number, the Reynolds number that you can cover also goes down. So this is important to remember. Whenever you see scalings like Reynolds cubed, that's only valid for non-reacting flows. For reacting flows, there's additional limitations from the chemical timescales. Yeah. Okay. So what do? We do modeling. That's our way out of it. We take direct numerical simulations, those equations that I gave you. We say, or we give up on our notion that we're going to resolve all the scales. There's no way to do that. We just don't have the computers. And even if you had the computers, perhaps designing aircraft engines is not the most effective use of those computers. So that's also something to think about. Maybe generating ChatGPT images is more important, right? So we don't know. That's how society thinks. We don't know. So we have to reduce our footprint, right, in how we build these things. So one way to do that is to take these governing equations and try to model out things that we are very sure about, so we can simulate something that's smaller in size, and that we can do on smaller size machines. We don't need this extremely large supercomputers. We can do with smaller ones. So this is the idea. So we want to do things like large eddy simulation and so on. Now, large eddy simulation, again, is a vast field. So this started as early as 1960s. There's a first paper by Smagorinsky, who was working on weather modeling for weather prediction. And he came up with the idea that you do not need to resolve all the scales. You can just model some of them. So that's the original idea for LES. And then folks at Stanford, Bill Reynolds and Parviz Moin, took this idea and then extended it to other kinds of flows, came up with models and so on, and that became known as large eddy simulation. And in the late 90s, others, Heinz Spitz, Norbert Peters, and others, took this idea of LES, extended it to combustion or turbulent combustion. And that's what we study now, or that's the thing that we care about at this point. So if you look at how LES has come into our worldview, it's because of many things that have happened, and we have to learn these individual aspects of this. We have to somehow figure out these things. So one of them is what are called manifold-based methods, which we will discuss tomorrow morning. So this is a critical aspect for modeling in combustion. There's the idea about numerical algorithms, which I will not discuss here. This is my expertise, but this is not relevant to turbulent combustion, so I'm not going to discuss it here. So you have to write these equations in a particular way, which makes it very effective for solving on computers and so on. So that's the other aspect of it. Now, there's a third aspect, which is what is called the in situ modeling. So this is very unique. There's only one other physics domain where you can do something like this. So LES has this unique feature that you can build the models from within the simulation itself. So you don't model ahead of time, you model during the simulation, which is a very unique concept. I haven't seen this elsewhere, until, of course, machine learning came by. I haven't seen this before. Yeah. So we want to address all three of this, okay? Not all three of this, the two of these. The other one I will not talk about. So the manifold methods we'll see tomorrow. What we want to look at is the in situ modeling, okay? So this means you first have to know what is LES, and then how do we do this in situ modeling in this. So we're at 4:05. So I think we should take like a 5-minute or 10-minute break.